This is lecture 6 on introductory quantum computing, and today we're talking about quantum teleportation. So last time I gave a brief preview to teleportation. We discussed the quantum no-cloning theorem, so we can't really copy a quantum state, but the idea of teleportation is that you can essentially move a quantum state. So suppose you have a qubit that has a particular state. Let's say psi is equal to alpha 0 plus beta 1. So we have a particular state for one qubit, and this state alpha beta in the computational basis. We want another qubit to acquire exactly that particular state. So the idea of teleportation is that there is one party who has a state initially in this alpha beta state. So let's call this party Alice. So Alice has access to a qubit, the qubit C, that's initialized in this alpha beta state. So initially, the state of qubit C is psi C is equal to alpha 0 C plus beta 1 C. Furthermore, there is another party that has access to another qubit. Let's call him Bob. So Bob has access to a qubit B. And we're going to talk about what it is initially. So initially, if qubit B is in one particular well-defined state, it's not entangled with anything else, then we won't be able to make that state equal to this. So teleportation makes use of the fact that initially this qubit B that Bob has access to is entangled with another qubit that Alice has access to. So the idea of teleportation is you essentially shift around the entanglement. So let's say there's this other qubit A that Alice has access to, and we initialize A and B in some entangled 2-qubit state. So our goal is that at the end of the process, whatever it is that we do, qubit B acquires a state alpha beta. So we want qubit B to become alpha 0 of B plus beta 1 of B. That's the goal. Final state of B, we want it to be psi B is equal to alpha 0 of B plus beta 1 of B. So we want this B to be at the end of the process, at the end of the teleportation process, to be unentangled with the rest of the system with A and C and have this particular state. And of course, the price we have to pay is that C will no longer be in that state because then we would have cloned B. So what ends up happening is that A and C form some entangled state with each other at the end of the process. Okay, so how is Alice going to achieve this? Well, let's pick an entangled state here. So, I start with this particular entangled state. Let's call it psi AB. We just pick one of the Bell states. We pick the first Bell state. So we pick phi naught of AB, which is 1 over square root 2 state 0, 0 plus 1, 1. So 0 of A tensor 0 of B plus 1A tensor 1B. So that's our initial state. And then Alice is going to perform some partial measurements on the 2 qubits she has access to. So she has access to A and C. And see, the idea is if she does this measurement in a basis such that the result, the projected result is an entangled state between A and C, after the measurement, A and C become entangled. And we can then show that B, for the particular choice of basis, becomes unentangled and takes a state that's either alpha beta or related to it in a way that we can very easily transform into alpha beta. Okay, so how should we proceed? Well, Alice performs the measurement in this Bell basis. So we argued in the last lecture that there are these 4 entangled states for 2 qubits that provides a very good orthonormal basis, and we can perform a measurement in that basis. So then, depending on the result of the measurement, the state of those 2 qubits gets projected to one of the Bell states. Okay. So first, before trying to figure that out, let's think about the initial state. So we're saying the initial state before doing any measurement is this phi 0 AB, one of the Bell states for A and B. Those are the 2 qubits that are initially entangled. And I'm going to tensor that with psi C. This is the state that Alice has in her possession. This is the alpha beta for qubit C. And she wants to send this to Bob. She wants Bob's qubit, this qubit B, to acquire the same state at the end of the process. All right, so if I do this tensor multiplication, let's write this in matrix form. So the representation of phi naught, again, our basis is 0, 0, so 2 qubit basis is 0, 0, 0, 1, 1, 0, 1, 1. So this state that's 1 over square root 2, 0, 0 plus 1 over square root 2, 1, 1. This is going to be 1 over square root 2, 0 for 0, 1, 0 for 1, 0, and 1 over square root 2. And then we're tensoring that with alpha beta, which is the state of qubit C initially. So that becomes, going to multiply this element by alpha beta. So I'll get alpha over square root 2, then beta over square root 2. Then I multiply 0 by alpha beta, so I get 2 zeros. Multiply this other 0 by alpha beta, 2 other zeros. And this 1 over square root 2 by alpha beta, so I get alpha over square root 2 beta over square root 2. This is my state in the basis, let's say sigma A, sigma B, sigma C, right? So we're doing A comes first, then B, then C, that take the following values. So if I write the associated basis vectors here, this is going to be 0, 0, 0. This is 0, 0, 1. This is 0, 1, 0. This is 0, 1, 1. And then the next one, so I'm going to pick this one and then put 0 and 1 in front of it. So it's going to be 1, 0, 0, 1, 0, 1. And finally, I pick this one, 1, 1, and I put 0 and 1 in front of it. So they're being tensored. So these basis states are tensored with the 0 and 1 of of the C qubit. So 0, 0 comes at 0 and 1, 0, 1 comes at 0 and 1, 1, 0, 0, 1, 1, 1, 0, 1. So in that basis, that's my initial state. All right. So if I want to write it in some expanded Dirac type notation, I would write my initial state. So let's call it psi initial is going to be alpha over over square root 2. Then I have 0a zero B 0 C. Then we have plus beta over square root 2. And then that's 0a, 0b, 1c. And then I have alpha over square root 2. It's this one, it's 1a, 1b, 0c. Finally, beta over square root 2 times 1a, 1b, 1c. All right, so that's our initial state. We could have just written it using this tensor product, right? So we could have, here we have 0, 0, and then it gets tensored with 0 and 1. So then we get 0, 0 with 0 comes with an alpha, 0, 0 with 1 comes with a beta, and then we have 1, 1, so that gets tensored with alpha 0 plus beta 1. So 0, 0 comes with a 0 and an alpha. Sorry, 1, 1 comes with a 0 and an alpha. 1, 1 comes with a 1 and a beta. Now, the next thing we want to do, or Alice wants to do, is that she wants to perform a measurement on A and C. So it's going to be useful to rearrange these and write our state in a way that the B goes to the end. So we essentially change the order in the tensor multiplication, the computational basis. So our state is, again, it's kind of a reordering of, or a permutation of basis vectors, if you wish. But it's going to look like this. So I can write alpha over square root 2. Now I switch B and C. Again, that's the same state. So 0, 0, 0 can be interpreted as 0 of A, 0 of C, 0 of B, plus beta over square root 2, 0 of A, 1 of C. So I pick this other permutation of qubits to write my basis states, and 0 of B, plus alpha over square root 2, 1a, 0 C, 1b, beta over square root 2, 1a, 1c, 1b. Okay. Now, Alice wants to perform a measurement in the Bell basis for A and C. So we can write, let me write it, again, it's identical, but I think it's going to be a little bit more useful. So I write this again as alpha over square root 2. Then I have the 0, 0 of AC with 0 of B. I have 0, 1 of AC with 0 of B. I have 1, 0 of AC, 1B, 1, 1 of AC. So the idea is each of these, like 0, 0, is going to be some superposition of, for example, phi 0 and phi 3, right? This is going to be a sum of two Bell vectors. Similarly, this is going to be a sum of two vectors. Each of those AC basis states in the computational basis. So the pair here is going to become some superposition of different Bell states. So Bell states are these entangled linear combinations of these basis states in the computational basis. And then if we collect the terms, then, for example, one of the Bell states gets tensored with some superposition of 0 and 1 for qubit B. And that superposition has coefficients that are alpha beta, maybe alpha minus beta, maybe beta alpha, but are related to alpha and beta and encode the same information as alpha and beta. So when Alice performs this partial measurement on A and C, then she's going to pick only one of these terms. And when she picks one of those terms, well, that automatically kills any other term that has a different Bell state in this entire superposition. So what it does, it forces the state of qubit B to become a particular single qubit superposition. Okay. So far we arrived at this expression, and so far we haven't done any measurement. It's nothing. It's just we kept massaging this initial state that still, this state written this way is still the same as that initial state. It's like a pure single qubit state for qubit C. And there is this entangled state for AB. So still in this form, even though it may not be very transparent because we put A and C together somehow, but there's nothing. This is still a tensor product of some state alpha beta for qubit C with the first Bell state for qubits A and B. Just wrote it in a more convenient way. All right. So let's remind ourselves what the Bell states were. So as a reminder, we said the first Bell state is 1 over square root 2, 0, 0 plus 1, 1. The next one is 1 over square root 2, 0, 1 plus 1, 0. The next one is 1 over square root 2, 0, 1 minus 1, 0. And the last one is 1 over square root 2, 0, 0 minus 1, 1. So from this, we can invert that and write these computational basis states in terms of the Bell states. So if I take, for example, the first and last one and add them up, I cancel out 1, 1. And then I find the sum to be 2 over square root 2, 0, 0. So 2 over square root 2 is just square root 2. Then that means that 0, 0 is 1 over square root 2 times phi naught plus phi 3. Okay. So now if I want the 0, 1 state, I play the same game with 1 and 2. I add them up. So 0, 1 is 1 over square root 2 phi 1 plus phi 2. If I want the next one, the 1, 0, I now subtract this phi 2. So 1, 0 is going to be 1 over square root 2, 1 minus 2. And finally, 1, 1, I'm going to look at 0 and 3 and subtract 3 from 0 to cancel out the 0, 0. So that's going to be 1 over square root 2, 0 minus 3. Okay. So we know what these are in terms of the Bell states. And we have this expression for our initial state before performing any measurements. So if we're performing measurements in Bell basis for qubits A and C, as Alice is doing, we should write the states in terms of the Bell state. So let's do that. So I can go here and write my psi initial. I can write it as I had alpha over square root 2, then 0, 0 of AC. So 0, 0 of AC, we said, is 1 over square root 2 phi naught plus phi 3. And that whole thing is tensored with, so it's implicit that the phi's are for AC. I can even write it if I want. And then that whole thing is tensored with state, I believe, state 0 of qubit B. Then the next term is going to be beta over square root 2. Now I have 0, 1 of AC. So 0, 1 of AC is 1 over square root 2 phi 1 plus phi 2, both for qubits A and C. And that's multiplied as a tensor product with 0 of B again. Then I have again alpha over square root 2. Then I have, now I have 1, 0 instead of 0, 1. So 1, 0 is going to be 1 over square root 2. Now it's phi 1 minus phi 2. So here I have 1B. And finally, the last term is going to be beta over square root 2. Now I have 1, 1. So 1, 1 is going to be 0 minus 3. And then that's multiplied by with 1 of B. Okay. So that's going to be, again, my initial state. I keep rewriting it in a way that allows us to easily find the post-measurement state upon a measurement in the Bell basis on qubits A and C. So this measurement is the key to teleportation. It's a measurement in a different basis, not in the computational basis, but in an equally well orthonormal basis given by these 4 Bell states, each of which is some linear combination of states in the computational basis, and each of them is entangled. All right, so what can we say now? So let's rearrange these terms again. So if I look at where I have psi 0, it appears here and here, right? It's only appearing in 2 places. So I can now recombine these. So yeah, so 1 over square root 2 times 1 over square root 2 just gives me a 1/2. So then I find I have a 1/2, let's say. Then I have a psi 0 of AC, and that's tensored with now. I have an alpha 0b from here, and I have a beta 1b. Okay, so I pick this term, this multiplying that, this term, I combine them into these terms. Then I play a similar game with, let's say, phi 1. So again, phi 1 appears, let's say, here and here. So what does it give me? Well, it gives me, again, another 1/2 from these 1 over square root 2s. Then I write my phi 1. I do the tensor with now here, it has a beta for 0. And then here it has an alpha for 1. So this came from these 2 terms. Then I can do phi 2 again. Similarly, it only appears here and here. So let's do that. So I get plus 1/2 phi 2 AC. And what's happening here? So phi 2 is going to give me a beta again for 0 of B, right? And here, phi 2 gives me a minus alpha for 1 of B. And finally, let's do the phi 3. Again, it appears in 2 places, here and here. And the term we're left with is, again, 1/2 phi 3 Now, what do I have? I have an alpha for 0 here. I have an alpha here, a 0 here, and here I have a minus beta for 1. All right. So now what Alice does is she performs this measurement in the Bell basis. So she's going to find either some observable that corresponds to phi 0, or some result that corresponds to phi 1, or some result that corresponds to phi 2, or some result that corresponds to phi 3. But then the wave function should collapse in a way that after the measurement, anything that would give some finite probability of finding a different Bell state than what she already found is not there. So how do we do that? Well, so let's make a table here. And let's say, or let me. So let's say Alice's measurement outcome. So she either finds in that measurement that AC is in state phi 0, or phi 1, or phi 2, or phi 3. Now, what happens? Well, if she finds this phi 0, then any of these terms that have a phi 1 or phi 2 or phi 3 give a finite probability of finding phi 1, phi 2, or phi 3. So the state should get projected only onto this. So we have to first kill them, and then we have to fix the normalization. So we see that 1/2 shouldn't be there because phi naught is already normalized and alpha beta is normalized. So the state, so post measurement projected state becomes, in this case, it becomes 0 AC tensor, let's say this guy, alpha 0, beta 1. In this case, I find 1 for AC. I have to kill every other term that would give a finite probability of finding a different Bell state. So this is going to be this tensor beta 0 plus alpha 1. This measurement outcome gives phi 2 AC tensor beta 0 minus alpha 1. Finally, the last one gives phi 3 AC tensor with alpha 0 minus beta 1. So now each of these is a tensor product of something for AC and just a single qubit state for B. So that means that after this measurement, B is not entangled with the rest of the system. The state of the whole system is just a tensor product of something for B with something for the other stuff. So qubit B has a well-defined state that we can read off from here. So post-measurement psi B, and let's write it in 0, 1 basis. So in this case, it's going to be just alpha beta. So if Alice performs this measurement in the Bell basis and finds phi 0, then we're done. Then Bob has that state. Now, what happens in this case? Well, the state of Bob is going to be, it's not going to be alpha beta, it's going to be beta alpha. In this case, the state of qubit B that Bob has access to is going to be beta minus alpha. And then in this case, the state of qubit B is going to be alpha minus beta. Alpha minus beta. So something quite mysterious has happened, right? So initially, Alice and Bob shared this entangled state for qubits A and B, and then Alice had some other qubit C in some state. And then the only thing she did, she performed a measurement on the 2 qubits she has access to. But one of those qubits was initially entangled with qubit B that Bob has access to. So, but the result of this, because anything that's then inconsistent with the result of Alice's measurement should be projected out, is that seems, as far as B is concerned, qubit B is concerned, previously it was in some entangled states with A, it did not have its own state, but after the measurement, it just has one well-defined single qubit state that's not entangled with anything, because the state of the whole system is some stuff tensor product with just this one state for qubit B. So that's one of the really mysterious aspects of entanglement and quantum mechanics, because it could be that this entangled pair, right, A and B, are really far away from each other. So you could prepare these 2 entangled states here and separate them. We didn't say anything about where they are. They could be miles away and still be in that entangled state. And then somewhere over here, Alice performs a measurement, and then immediately we're saying something is changing, right? The state of qubit B is going to be just this particular single qubit state. So that was something that really bothered Einstein, right? Because we know information cannot travel faster than the speed of light. So what's happening is that change in the state of qubit B inconsistent with relativity? Is information instantaneously traveling from Alice to Bob? Well, not exactly, because, well, no, right? Because Bob doesn't know what Alice measured. So Bob, after the measurements, can have, as far as Bob is concerned, he's living in his own world with his qubit far away from Alice. As far as he's concerned, he either has, let's say, a qubit that's entangled with a qubit far away, or he has one of these 4 states, each with some classical probability. It turns out that mathematically, there's not going to be a difference. As far as Bob is concerned, if you perform measurements only on qubit B, Bob won't be able to tell apart these 2 scenarios. So being entangled with something else far away, as far as Bob is concerned, is like being in some mixture with some classical probabilities of different states for his own qubit. So right now, this measurement is done. We're saying that state changed, but Bob doesn't know what it is, and any measurement he can do won't be able to tell the difference between that initial entangled state and then this classical mixture of single qubit states, each with some probability. So there's a mathematical framework to describe this known as the density matrix. So whenever you're in some classical mixture of different states, you're in some, you cannot use quantum states, but you have to use this other object, which is a classical mixture of them. It's known as the density matrix. And if you have a qubit or some quantum system that's entangled with something else, and you only have access to this part of the system, again, the correct description would be to trace out the qubits that are somewhere else and you don't have access to, and then you end up with some reduced density matrix, or some density matrix for just the qubit or the system you have access to. And then these are going to be the same. So the probabilities of whatever you do will be the same. So right now this happened. Bob doesn't know which one he has, but he has one of these 4 states, and they're very close to alpha beta. One of them is alpha beta. And then the other ones, again, have alpha and beta, those real numbers, which we were not able to know to infinite precision. It has a qubit that has those real numbers in it. So now here comes the information transfer. So Alice now needs to make a phone call to Bob and tell him, hey, Bob, I performed this measurement and I found phi 1, or I found phi 3 or phi 2. And then after this information is passed to Bob, which cannot travel faster than the speed of light, Bob knows which state he has. Then he knows how to transform that state to alpha beta. So how are we going to proceed? Well, so let's make another table. So now let's say Alice's phone call either says phi 0, phi 1, phi 2, phi 3. So then Bob can apply a unitary operator. He can form some gates and apply it on his qubit. And he knows exactly what to do. So let me write some U here. It's a 2x2 unitary that Bob just creates and applies to his qubit. So in this case, that U is the identity. Do nothing. You already have the state. So then let's call it U0. Let's say Bob's unitary. So he applies this unitary operator and then Bob's final state. Well, not Bob's state, but the state of the qubit B that Bob has access to. So that's going to be U1 times alpha beta. Sorry, U naught alpha beta. That's just the identity. So alpha beta. Essentially do nothing. Applying the identity is like do nothing. Okay, so what was the next one? The next one is beta alpha, right here. So Bob wants to flip these. So he wants to go from beta alpha to alpha beta. And this unitary 1, 1 on the off diagonal is going to do that. So let's do this 0, 1, 1, 0. Beta alpha, right, is the state that Bob's qubit has after the measurement. So let's do that multiplication. 0 times beta, 1 times alpha gives me alpha. 1 times beta plus 0 times alpha, that gives me beta. So that's good. So what if Bob's state is the next one is beta minus alpha? Well, there's again another unitary operator that does it. So you put 0, 1, minus 1, and 0. And just apply that. So you transform the state you already have by a unitary operator you can create and apply to your qubits. So 0, 1, minus 1, 0. That gives me alpha minus beta rather. Sorry, it's beta minus alpha, right? It's beta minus alpha, and then it gives me what does it give me? Give me minus alpha minus beta, which is essentially the same. It's the same as alpha beta up to an overall phase, which doesn't matter. What if I if I want to fix the phase, well, I just put a different unitary here. Put the minus 1 over here. This is beta minus alpha. So then it gives me alpha beta. And finally, if I want to do, so U3, if I want to transform alpha minus beta, I just put 1 and -1 on the diagonal. So 1, 0, 0, -1 changes that to alpha beta. And we can easily verify that these are unitary operators. Let's take U2, for example. So then U2 dagger, these are real, so it's going to be its transpose. So it's going to be 0, -1, and 1, 0. So what is U2 dagger U2? It's going to be 0, 1, -1, 0. 0, -1, 1, 0. So if I do that multiplication, I find 1 here, 0 times 0 plus 1 times 1. I find 0 here. I find 0 here. Here, I find -1 times -1 is 1, plus 0 times 0 is 1. So that product is the identity. So all of these are unitary operators. So as soon as Bob receives the phone call with the information of what Alice measured, he no longer has a classical mixture of these states without knowing which one. There's just some probability for each. He knows for sure that he has one of these, and then that information enables him to perform a given transformation on the state, and the result will be that at the end of the day, this state alpha beta that initially qubit C had is now the state of qubit B that Bob had access to. So essentially, at the same time, like that state was copied to qubit B, but it's not cloning because now it's erased. Qubit C is now in one of these Bell states, so it's in some entangled state with qubit A that was initially, before doing any measurement or unitary transformation, was entangled with Bob's qubit. All right, so that's a really cool application of the things we've learned so far. So it made use of the representation of multi-qubit states, measurements in different spaces, and also partial measurements when you perform the measurement on just part of the system, and the unitary transformation of states.